Hey guys, well, I'm back out in the shop today doing some accuracy test on the impact tolerant touch probe from Hallmark Designs. Please excuse the background noise. I've got a portable AC running. It's just unbearable without it. The first thing I want to do is make sure that there's no run out on the touch probe. I've rechecked it. I've had too numerous to count the crashes I've had already developing the probing routines. So I wanted to kind of recheck it and make sure that everything was okay. So in today's video we're going to be doing some accuracy test, and the first thing I want to do is make sure that there's no run out on the touch probe and everything is following the spindle center line. Now, one thing I've realized over the last few days doing numerous tests is because of the design of the contact surfaces in the impact tolerant touch probe, you really only need to concentrate on one 90-degree quadrant. That's with checking for run out and also doing probing. You can see here that I've got it dialed in. There's no run out whatsoever on the touch probe. So once we verify that there is no run out, we can check pre-travel. Okay, so the first test is to check pre-travel, and I'm going to just probe into the work and see how much deflection when the needle stops. See how much deflection we have. Okay, you can see we're resting on the cheap dial indicator here. Okay, so in order to check pre-travel, we want to just simply type in on the MDI line under the MDI tab G31 Y 1.0 F5. G31 is a probing move, and it will stop as soon as the probe makes contact. I'm going to probe in. Okay, it stopped, and it looks like we are at 1.5 thousandths, 0.0015. Okay, I'm going to turn it about 10 degrees. Go again. Still about the same, about 1.5 thousandths. Back off again. Back off. I'm going to turn it again, 10 degrees. Thereabouts approximately. Again, 1.5 thousandths. Back off. Turn it again, about 10 degrees. Okay, that creeped up a little bit more, maybe 0.0018. If I had to guess. Okay, we're going to back off. Another 10 degrees or so. Maybe 0.0019. 185. Back off again. Get another 10 degrees or so. Alright, that looks more like 2 thousandths, so we'll call it 2.002. Back off. Another 10 degrees. Again, 2 thousandths. Turn it again. Another 10 degrees. Again, that's around 2 thousandths, maybe 0.0021 if I had to guess. Apologize for my cheap Chinese indicator here. Okay, and then now 90 down to 180 degrees. And again 0.0021. So for our pre-travel for this 90-degree quadrant, it appears as though we have anywhere between 0.0015 and 0.0021. So anywhere between 3 to 4 thousandths total pre-travel. You have to take into account both directions, so that seems to be pretty much in line with what I saw on Hallmark Design videos in the setup guide and the operator's manual. Now, he goes into more in-depth and more details on setting up for pre-travel and checking it far better than I could. So make sure you check out those videos. So now that we know what our pre-travel is, let's start doing some accuracy tests. First, I want to kind of go over some important things that you should be aware of when using any touch probe, really. Number one is you want to indicate the touch probe in the same orientation every time you use it for better accuracy. So if you're going to have your cord going out at 90 degrees, indicate that. Likewise, you should have a way to disable your spindle motor. Now, I originally installed a key switch here to turn off the spindle. However, I found that the key was cumbersome. It kind of hung in the way of the e-stop, so I switched it out with just a switch that I can turn off or on. So it's good to have that, because you don't want the cord whipping around and causing any issues or damage to the probes. For the first test, I want to first make sure that we get the pre-travel set correctly. Now, we measured anywhere between 0.0015 and 0.0021. So if we go with the highest reading, we have about 0.0042 of pre-travel. So we're going to take that information and we're going to set that up in our tool data. Okay, so we want to set that up in our tool data. So here is our tool information. I have set up my touch probe as tool number 99. I figured my offset in the first video, and so the diameter, taking in consideration the pre-travel, I came up with 0.1538 is what it really should be according to my pre-travel measurements, but I've done a few tests already and it came out to be 0.1534. Now, I'm not sure about all the different machines and software probing routines that are out there, but the way I've gotten my probing routine set up is I made a couple of changes from the first video. The first thing you might notice is I added this probe feed rate. This is a user-defined DRO, and you can use this to help determine at what feed rate your particular machine gets consistent results. This particular machine, I've done a few tests here, and at 30 inches per minute I can get consistent results. Having this user-defined DRO kind of helps you get the best results for your particular machine. So that is something new that I recently added. Also, I'm going to be probing the inside of a bearing. The reason being is I know this particular bearing is 15 millimeters internal diameter, which is 0.59055. So that way I can check the accuracy without any question. So one thing good about these particular probing routines is for the OD and ID routines, I have this stock hole diameter DRO. This DRO serves two purposes. When probing the outside dimension, you just simply type in the approximate dimension. If you're probing something that happens to be 1 inch in diameter, then just simply put in 1 inch, and it doesn't have to be perfect, just needs to be close, and then that way it will probe it, and it saves you a lot of time probing, and you don't have to have a probing routine that searches or seeks. Next, this particular DRO will output the dimension that Mach 3 gets as its result. So this is how I am checking the accuracy of my pre-travel, and it's fairly close. I measured 0.0021, so you double that, which gives you 0.0042, and after doing some probing tests I ended up with 0.0046. So pretty close. So let me show you how I came up with this result. Okay, so here is my bearing. The internal diameter is 15 millimeters, and we're going to probe it at 30 inches per minute. Okay. Alright, you can see we're at 0.5906. So what I want to do now is just run about 10 probes at 30 inches per minute, and we'll record our results, and we'll see how consistent we are. Alright, let's look at the results. So I ran 10 tests. Get the shadow off here. Alright, so I ran 10 tests at 30 inches per minute, and they were all consistent except the first one, which was 0.5908. All the rest were 0.5906, which is really good and consistent. Now let's probe the outside diameter of this bearing. Okay, so now we're going to probe the outside dimension of the bearing. This bearing is 35 millimeters, which is 1.37795. Again, we're going to be using the outside dimension probing routine. Now, whenever you're using this particular routine, you want to input the approximate size of the stock, and don't forget to put in your feed rate. Again, we're going to run about 10 different probes, and let's see what we get, and we'll record our results and see what we find. Okay, after 10 probes on the OD, you can see the results. Still really consistent, 1.3780, and those were the most of the measurements, and 1.3782 happened 4 times, so about 60-40, I guess. But the variance is very, very small, really accurate, and I'm really happy with the results I'm finding. So you can see from these tests that very reliable and very consistent results with the impact tolerant touch probe. So the next test for accuracy that I want to check is doing the Z negative probing routine and finding the top of the stock. This is probably going to be one of the more used probing routines, so I definitely want to check and see what the accuracy is for this particular routine. Now, the touch probe is always going to return a measurement of 4.8475. Because the particular macro moves 1 inch above the part after it checks the Z0. So we're going to use our machine coordinates, and this will always give us the exact measurement from our home switch. So this number right here will vary after each probe. Alright, so we're going to be doing our first 10 probes at 25 inches per minute, and we'll record all of our data here, and we'll see what kind of results we get. I'm also going to vary the start height just to try to get some consistent results. So here we go with the first. Alright, let's check our results. Alright, at 25 inches per minute, it looks like our lowest reading was 7.6249, right there in the middle. There was a couple. And then our highest was 7.6254. So the difference between our lowest and highest reading is 1/2 thousandths of an inch. I would say that that is pretty accurate. Alright, so that's at 25 inches per minute. Let's try 55 inches per minute. We'll do the same routine and we'll see what we find. Okay, so we'll type in 55 inches per minute in our DRO and record our results. At 55 inches per minute, we're getting readings around 7.6256 and 7.6259. A difference of 0.0003. So less than half a thousandth of an inch. Pretty consistent. The Z probing routine is only going straight down, so I would expect to get more consistent results with the Z probing routine. But even with the inside dimension and the outside dimension, you can get really accurate measurements. So if you want to do some, set up your part and find, say for instance, this corner. Now you want to park the probe about a ½ inch in from each side of the stock, as well as a ½ inch above. The probing routine will find your Z, set your Z height, and find the corner. Just like that. And now we have referenced our part, and we can start machining. We have also set our Z height. If we turn our tool offsets on, you will see that we're about a ½ inch above the part. So you can see with these results, the accuracy of the impact tolerant touch probe far exceeds my expectations. I'm very satisfied with these results. I want to take a minute to kind of go over just the basic wiring of the impact tolerant touch probe. The impact tolerant touch probe is just a simple, normally closed set of contacts inside the probe itself, and it just basically needs a 2-wire hookup. Most breakout boards supply 5 volts and 5 volts on the return side to your input. I happen to be using input 15. You want to set up your Mach 3. Make sure your probe is active. This is up under ports and pins, input signals. Enable the probe. Set it up for port 1. And again, whatever pin you're using as your input signal. I'm using pin 15. And you want to set it up for active low. The probe is designed in a rest position to make contact. So 5 volts will always be going to the input. So this input will be high in a normal state. And when the probe contact is made with the probe, this signal will go low. So you want to set it up for active low. This is so the probing routines can check to make sure that this probe is not tripped. And the only way to really do that is have this as a normally closed set of contacts. Now the connections I went over in the previous video specifically for my machine. However, it's just a 5-pin DIN connector. You can pick up a 5-pin DIN socket online. And we're going to be using pins 4 and 5. Now these are standard pins used on a MIDI connector. And here is your standard MIDI connector, and again pins 4 and 5. So if you need an extra long cable for whatever reason, you can pick you up just a basic keyboard extension cable with 5-pin DIN connectors on each side. This one I picked up was 10 feet, and they come in 3, 5, 10, and 15 feet lengths. So if you need an extra long cable, you can simply just clip the end off and wire it into the probe. It does come with a 6-foot length cable for non-Tormach owners, and I think for Tormach owners it comes with a 3-foot cable, because their DIN connector is right there inside, right beside the mill. You want to store your impact tolerant touch probe in an upright position. So I decided, why not take this opportunity to design and 3D print a nice little storage case for the impact tolerant touch probe. So you have clearance here for the stylus. I did a little engraving in there and also made a nice cover with the serial number of my touch probe. This is 417. So now I can keep it nice and secure, keep it out of the elements, and store it when not in use. Well, I guess that wraps up this video on the accuracy test for the impact tolerant touch probe. As you can see, this is a very accurate, not to mention the ability to be crash resistant is something that I really do need. If you're interested in one of these impact tolerant touch probes, you'll find the link in the video description where you can find more information and also get in touch with Hallmark Designs. If you have any questions or suggestions for more advanced probing routines, please feel free to comment. If you're interested in any of my CNC conversion plans or the automatic tool changer, screen set, and macros, you can find that information on the website. Thumbs up if you liked the video. Thanks for watching. Please subscribe, and most importantly, be safe.